Hello everyone, I'm very honored to be invited at FinAI for my presentation. My name is Zhuohan. I'm currently a postdoc researcher at Mohamed bin Zayed University of Artificial Intelligence in Abu Dhabi, working with Professor Nakov. My research interest was on fact-checking and now actively moving towards financial AI. Especially we are building financial reasoning benchmarks and also no-resource financial LMs, such as Arabic and Hindi. Today, I present our work at NACO this year regarding fact-checking, named FIRE, Fact-Checking with Interactive Retrieval and Verification. In short, FIRE. For me, I'm particularly interested in bridging these two areas, fact-checking, especially in the finance domain. Here are the contexts if you are interested and would like to collaborate on this. I will first give a little background about fact-checking. Nowadays, it is very important to fact-check a long document, especially they can be easily generated by AI systems. However, fact-checking the whole document is really challenging. Therefore, recently, it is quite usual to break down the process into several steps. First, decompose the entire document into multiple atomic claims. So atomic claim means it is a simple, standalone factual statement that only expresses one piece of information. Second, filter out uncheckworthy claims. Then, fact-check each atomic claim. Last, integrate factual of all atomic claims as the final verdict for the entire document. In this work, we focus on such important steps. Fact-checking each atomic claim, since it is shown that this is the most tricky one in the previous work. The definition is quite simple. Given an atomic claim, determine whether it is factual or not by producing a binary label, true or false. To do that, previous approaches such as FactCheck GPT or Fact2 that are shown in the blue rectangle first prompt an LLM to generate n search queries, usually 5, at the same time, and they use this to search documents online and come back as evidence. And then they use the evidence to make the verification. We believe there are two issues with such approaches. One is that it does not use the LLM's internal knowledge enough, especially now LLMs have been trained on vast amount of knowledge. Therefore, they can process enough knowledge that are sufficient to make the verification without external knowledge. Like the example we show here, since we all know Taylor Swift is a quite famous American singer, LLM can make the judgment directly without evidence search. Another problem is that we believe such approaches do not mimic the way humans search online, which we usually search sequentially, not concurrently. This means, for each claim, we usually think of one search query first and get the search results. Such results can influence us to think of better search queries. For instance, in this example, the second results contain a keyword false. That makes us to think of the key search queries and eventually find the key evidence for the claim. So to address these two issues, we propose FIRE, as shown in the green rectangle. Now when we input a claim, the LLM will try to verify it first with its own knowledge. If LLM determines it is enough to make the judgment, it can produce the final label directly. Otherwise, it will generate a new search query, which uses all the previous search results as the condition, and tries to generate the search query that aims to obtain additional knowledge for the claim. This will form a loop until the model is confident enough to make a judgment or it reaches the maximum threshold, which we will have the final verification without any more search. Similar to us, there is a contemporary work called SAFE, it's shown in the middle, that conducts the interactive searches as well, but it still separates the search and the verification paths, while we conduct both interactive search and verification. Regarding the experiments, we use these 4 datasets, where we use FactCheck Bench as our dataset, and then we test the generalization capacity on other 3 datasets. For language models, we test these different models from both open source and proprietary models from various model families. So our first finding is that GPT-4 Mini is good enough. It is only slightly worse than the most advanced models, such as GPT-o1 and the Cloud Sonnet at that time, but it is so much cheaper. So after testing with all these models, we find there are certain problems. For example, sometimes LLMs keep generating the repeated search queries. So to mitigate these issues, we propose two approaches. One is called early termination, which we will early terminate the interactive process once we observe the similar queries or similar search results. And the second is to call the diversity prompt, which we specifically add additional prompts to encourage the LMs to generate more diverse queries. And we find that we should early stop once the search results are too similar, because in that case, more searches will not help. And another issue we observe is that sometimes LMs might be overconfident, which cause it does not search at all and make all the judgments only based on its own knowledge. In such case, we also tried two approaches, including we called at least one or at least two, which requires the LMs to make at least one or two evidence retrieval. And the second, we call the inclusive prompt, where we specifically prompt the models to be less strict, open-minded, and avoid being overconfident. However, our experiments showed that the forcing LMs to search more does not help. It might even introduce noise, which might impact the performance. So after these preliminary studies, we compare our framework to others, which we explained before. We also add two baselines called random and always true or false. We see that most frameworks can do really well by achieving around 17 to 19% of F1. And our framework with GPT-4o has the slightly better performance by winning 7 out of 18 metrics. However, in terms of cost, our framework is so much better. Averagely, we can save like 7.6 times LM cost and 60.5 times the search cost when we are using the GPT-4 Mini, which highlights GPT-4 Mini has enough knowledge and the capacity to verify most of the claims. This also shows that our framework has the potential to be applied to large scale for production in the real world. So our ablation studies shows some interesting findings that GPT-4 Mini is more confident compared to GPT-4o. It's because it conduct less search, like we show here in this bin check dataset. GPT-4 Mini verify most of the claims without a search. Well, for GPT-4o, it still have 25. It is only like a small number of claims is verified without search. However, when we do not allow them to reason to specify its reasoning trace, the confidence both drops, especially for GPT-4 Mini. Now, no claim can be verified without search or requires at least one search. This means now when it's not output its reasoning trace, it becomes less confident to depend on its own knowledge. So GPT-4o is also impacted, but not as extreme as the GPT-4 Mini. At end, we have also conducted some error analysis where we manually classify all the wrong cases into 9 fine-grained types under 4 major issues. So we find the most problematic is the knowledge issue, especially about the insufficient knowledge, since some claims might contain multiple aspects, which we code is not atomic claims at the beginning. And there are some issues regarding the current benchmarks, including sometimes it's not a claim, it's just a name, and the claim is ambiguous or unclear. And sometimes we find the original label is just incorrect. And so we believe there's still a long way to improve the benchmarks. And also, as we find before, like these models can achieve around 90% of performance. So it might show the benchmarks are already too easy. And we also find some interesting things about the reasoning part, especially the LMs tend to be very strict regarding its reasoning, especially for the GPT-4o or GPT-4 mini. So they try to rely on the strict exact match. So for instance, here, like word class puzzle and fun word class puzzle. So basically, the LM will say it's not the same. So to summarize, we propose a simple but cost-efficient framework for fact-checking, which significantly save both LM and search costs. So in the future work, we will try to improve the fact-checking benchmarks, such as filtering out non-claims, correct gold labels, and annotate more complex claims. We also are trying to integrate a memory bank, such as a fact-checking product might encounter similar claims all the time, so you will be more efficient to directly retrieve the results instead of conducting the whole pipeline again. Yeah, so I think that's all. Thank you very much. Yeah, if there's any questions.